Okay, so let's go through galvanic cells. As an example here, I've just got a hydrogen and silver cell. So because the hydrogen has been used in the cell, it's going to be the anode for the cell. And we're going to write it down like that in terms of the cell notation. So let's just have a look what's happening on the cell first, and then we'll get into writing out a net ionic equation. So we'll see we've got hydrogen gas coming in here, and this is our piece of glassware with the wire coming straight through and a platinum anode on this side. So the hydrogen gas is obviously going to be what's coming in on that side. The platinum, the reason why we use a platinum anode is because we always need our electrodes to be made of a solid, and we obviously need that to be inert. We don't want it reacting with any of our reagents instead of the reagents themselves. So we need an inert conductor, and for that reason we're going to use platinum. So in the solution here we see we've got nitric acid, which means we've got hydrogen ions and nitrate ions present in solution. And don't worry about the balancing of that for now. That's just part of the balanced equation. And on the other side, we've got silver cathode. Even if they hadn't told us that that's the cathode and that's the anode, we would have been able to figure that out. And we've got a silver nitrate solution. So there's the silver ions, and then there are nitrate ions present. So the fact that I've got nitrate ions present in both solutions is probably a bit of a clue that that's going to be a spectator ion. But we'll look at the table nonetheless and just make sure about that. And so what we've essentially got is we've got hydrogen, we've got hydrogen ions, nitrate ions, silver, and a piece of platinum. So looking at that on the table, we can, I'm just going to move it to there. So let's see what we've got. We've got hydrogen gas over there, we've got hydrogen ions over there, and then we've got silver ions, and we've got silver on that side. Now in terms of the nitrates, so the nitrates are there, I'm just going to move this for a sec. So they're the nitrates. So there's that nitrate. There are hydrogens present for both of them if necessary, but we don't have any nitrogen dioxide or nitrogen monoxide. So that tells us that it can't be those reactions because we're separating the two half cells, you need all of the ingredients on both sides in order for the full reactions to occur. So that's how we know that it's only going to be the silver. Plus, the same reason, there's our platinum. And although our platinum is a really weak reducing agent, which is part of the reason why we use it, we don't have platinum ions present anyway. So that tells us that that's not going to take part. So whenever you're doing any of these reactions where it's been separated into the two half cells, make sure that you can make a full rectangle before you start. And then you're going to look at using the table. So which one's highest on the right is this one, so take this one away. Which one's lowest on the left? It's going to be this one, so take this one away. And there's going to be our spontaneous reaction. So remember, because it's the hydrogen, the standard hydrogen electrode, we're going to use it as the anode anyway. And in this case, it is the anode because it's undergoing oxidation. It's going from right to left. If it had been the other way around, we would have known it would have actually acted as the, or undergone reduction, but we would have still written it down as the anode because we're using it as the standard reference electrode. But for us, we're going to be able to just do it like this. So going back to this image, you'll see that's why for oxidation, which I'm going to highlight orange, we're going to have that hydrogen coming in and going into the cell as hydrogen ions with the electrons. And on the other side, we're going to have our silver gaining electrons, so the electrons flow through the external circuit through to the silver cathode, and they are going to pick up those silver ions in solution and be converted to solid silver, which will then plate on the outside. So you're going to have that plating of silver. So this side is going to increase in mass overall. So this side is going to increase in mass, and that side is going to decrease in volume overall. So now we can definitely see that our nitrate ions are going to be our spectator ions in this instance, and our platinum, as we said, is our inert conductor for this particular reaction. Okay, so let's carry on talking about how these cells are proceeding. So as the reaction is going to proceed, we get that the hydrogen being converted into hydrogen ions. So the hydrogen is going to be our reducing agent. Hydrogen gas is the reducing agent. And the silver ions on this side, they are going to be the oxidizing agent. So it's very important to keep track of what everything is. So the platinum is the anode, the hydrogen is the reducing agent, the silver ions are the oxidizing agent, and the silver is the cathode. And there are going to be some cases where an anode and a reducing agent might be the same thing if it's a solid, but if it's a gas, like in this situation, then obviously you need a separate anode. So as the reaction is going to proceed, you're going to have an increasing concentration of hydrogen ions into the solution. So this entire solution is going to become a whole lot more positive. And on this side, we're going to take silver ions out of solution, and so the entire solution becomes a lot more negative. So that then introduces us to the salt bridge. So the salt bridge is going to be something that's going to perform two functions. The first is to complete the circuit, and the second is to maintain electrical neutrality in the half cell. So that's basically saying we don't want this side getting too positive and this side getting too negative. Otherwise, our electrons are going to stop flowing. So we want to maintain electrical neutrality. So I think of the ions in the salt bridge like paramedics rushing to an emergency, going to save the day. So this side is becoming a whole lot more positive. So as a result, we're going to take anions from the salt bridge, and those are going to flow towards the anode half cell. So that brings in those vowels and consonants that we spoke about before. So our two vowels go together. And then on this side, it's becoming a whole lot more negative. So we have cations from the salt bridge flowing towards the cathode half cell, and in order to stop it from becoming too negative. So please just be careful, don't say neutral, because we're not talking about pH here, but we're talking about charge neutrality. So to maintain charge neutrality, and that's where that explanation comes in. The other thing is, please don't say anions flow to the anode and cations flow to the cathode. That what I've written there is just a memory trigger for you. You need to say cations from the salt bridge flow to the cathode half cell to maintain charge neutrality. That's the full sentence. So in other words, I don't mean these cations are flowing to this half cell. I mean the cations in the salt bridge. Eventually, you're going to get some of these cells flowing through there and some of these ions flowing through there. But that's eventually what's going to happen. But the immediate action of the salt bridge is to do just this. And then obviously the size of the salt bridge is going to, properties of the salt bridge are going to predict or define what is going to happen in terms of how well the cell works. So you've approached the concept of internal resistance in the electricity section. Now we can look at it from the chemical point of view and go, this is the cell, this is the thing that's providing the electrical energy. And so how well the cell functions is going to be based on its internal resistance, the resistance that the electrons or ions are going to experience moving through here. So our electrons are going to move through the external circuit, and in questions they'll often ask you about electron flow, so be aware of that. And then our ions are going to flow through like this. So please remember, this is not a circuit like a Formula 1 circuit. They're not moving through like this. They're going electrons through the external circuit and the ions in the internal circuit. Remember conductivity? We want charged particles that are free to move. We don't care which way they move. We just need them to move. And so your salt bridge, we speak about the wider, shorter, and more conductive the salt bridge is, the lower the internal resistance. Think about my paramedic example. If you've got a whole lot of paramedics on a team and they've got to run through a wide corridor over a short distance, they're going to be able to get to their patient really quickly and help. If they've got to run down a long corridor that's far away and there's only one lone paramedic, it's going to be really hard for him to do his job. So the resistance that he experiences before he can even do his job is high. That's what internal resistance is. So when you come to speak about internal resistance of the salt bridge, that's what they're referring to. And the conductivity is saying how many ions are dissolved in that salt bridge. Remember, it's not literally salt. It's a salt solution that is inside that U-tube. It's literally called a U-tube and stuck with cotton wool. Okay, so when it comes to doing that net ionic equation, then what we're going to do, this one is obviously going to be multiplied by 2 because there's the one electron, and this side's only going to be multiplied by 1, so I'm just going to write it times 2 over here. So we land up with our H2 plus 2Ag plus is going to go to 2H plus 2Ag. And there again, this is the substance that is oxidized, and it is the reducing agent. This is the substance that is reduced, and it is the oxidizing agent. Neither of those two are going to be an agent. Remember, it's only an agent can only be a reagent. That's going to be your cathode, however. And because this is a gas, we need a separate anode. Okay, so talk about calculating the initial EMF of the cell. It's important when they speak about the initial EMF of the cell, it can only be initial because once the reaction starts occurring, your standard conditions are obviously going to change. So remember, when we're looking at our table, the standard conditions are that condition of temperature, pressure, and concentration. As the reaction starts proceeding, this concentration of silver ions decreases and that concentration of hydrogen ions increases, which means that those values are going to change. So when they ask you to calculate the EMF of the cell, they're asking you to use these values, but that's only under standard conditions, which is at the beginning. After that, they start changing. So when you're calculating your EMF of your cell, we're going to go E naught cell is equal to, you can go either E naught cathode minus E naught anode, or oxidizing agent minus reducing agent. It really doesn't matter, as long as you don't get confused in terms of the anode. So please don't read off platinum, the platinum value, because it's not taking part in the full reaction. So sorry, here's our reducing agent. And so what you're going to do is you're going to find them. So where we found our reaction, so there was our hydrogen and there was the silver. So our hydrogen obviously got a value of 0 and our silver's got a value of plus 0.80. So this from our oxidizing agent is the first one. So there's our plus 0.80 minus, and this value is just 0.00. And that's where we get a value of plus 0.80 volts, and that's where that reading is coming from. So that is an initial reading. As the reaction proceeds, that value is going to decrease as the reaction approaches equilibrium. The positive is just reminding you that this is spontaneous. It's a spontaneous reaction. So remember, when our E naught cell value is spontaneous, that's an indication that it's positive. Or sorry, when it's positive, it indicates that it's spontaneous. And then doing the cell notation, so this is just a way of, instead of drawing out the whole cell, that we're able to just do the cell notation, a single line, be able to write out exactly what's going on. I'm going to do this without phase labels just for the purpose of doing this. The SAGs give really, really good guidelines in terms of exactly how to write out cell notation. The basic rules are a single line to show phase change, and a double line to show a salt bridge. I use, to remind myself, I go ABC. So A is anode, B is bridge, and C is cathode. So we're going to start with our anode. So our anode is the platinum. You do like a giant W. So you go anode into solution, through the salt bridge, into solution, back to the cathode. So just to remind you about that. So our anode is going to be the platinum, single line. Then we're going to do our hydrogen and another single line, and then we're going to do our H+, and then double line for the bridge. So we've done anode now, and the anode half cell, and the bridge double line, and then I go in solution with the silver, Ag+, and then Ag. Okay, so just to remind you again that this is the anode, this is the reducing agent, the silver is the oxidizing agent, and the silver is the cathode. Overall, so in terms of what it is that's there. So this is going to be different for every cell. Don't learn this off by heart. But for a cell where you've got, first of all, the standard hydrogen electrode, it's always going to be on the anode side. And where you've got a gas, you're going to need to have a separate metal electrode present. I just want to show you quickly, have a look at the two half cells. So we've got hydrogen, then hydrogen plus, silver, ions, and silver. Hydrogen, hydrogen plus, silver, iron, silver. So if you've got your half reactions written out nicely, they follow exactly the same order to get into your cell notation.